I'm going to start if everything is okay. I'm recording, and today is the last occasion we have to work together in this format, after which, if you have questions, we have to contact me directly. I don't have much time left, and actually I've done 99, well, I've done most of what I was planning to do, but I have a feeling that what I would probably need more than 1.5 hours to finish covering the material that I would like to cover. So today, to see if that is more, it's probably faster, I'm going to use, I'm going to share a PDF with you, with my lecture notes for today. And I will try to lecture following that PDF. It's basically like a PowerPoint, except that since, as usual, it's lots of equation, it's better to share them on a PDF. But, as usual, I will send you the document afterwards. And in any case, as usual, stop me at any moment if something is not clear, okay? I might tend to go a bit faster. That's partly the purpose, because I would like to finish, I would like to tell you, to guide you through most of the surface wave concept that I think will be useful for you later on. So I'm going to share this document, which you should see now on your screen. And this document it's got, everything should be correct except for my email, which is an old one. I think it was older in 2015 when I wrote this. So, but everything else should be okay. So let's see. I'm going to do it like that. So I introduced surface waves last week already a little bit, and I think we went through what are probably the most important, well, some of the most important concepts. Surface waves are something that emerges anytime you have an elastic medium bounded by a free surface, a surface that is free of stress. We see mathematically how that can be proved, verified in a minute. If you look at a seismogram, which is what you see here, you see that the surface waves actually are the most energetic part of the signal. That's, like I was saying the other day, that's a consequence of the fact that geometrical spreading in a surface wave goes like r squared, where r is epicentral distance. And in a body wave, it goes roughly like r, sorry, in surface wave, it goes like r, and in body waves, it goes roughly like r squared, which means basically that energy gets quickly distributed over a very large area in body waves. And in surface wave, this phenomenon is slower as the wave travels away from the epicenter. So at significant distance, here you're at a distance of 110 degrees. So that's about like 12,000 kilometers or so. You see that the surface wave basically dominates all the three components of the seismogram. This is one seismogram, three components, okay, radial, transverse, and vertical. You see that the radial and vertical component of the surface waves are very similar, and the transverse one is slightly different. By the way, I should tell you what I mean by radial, vertical, and transverse. Vertical, which is the bottom one here, is easy. It's just, if this is the surface of the Earth, vertically is the direction that's perpendicular to the surface of the Earth. Okay, so then to define the radial and transverse components, you have to know where your observation point, your station, your instrument lies with respect to the source. So if you trace a great circle, or if you prefer to think in 2 dimensions, a straight line, okay, from source to receiver, the radial component is the component that points in the direction of this straight line. Okay, it points from the source to the receiver, and the transverse component is perpendicular both to radial and to vertical. So it's, you know, if you have a wave, I'm assuming that you can still see my
Joe.
that you can still see my face on the screen, okay? Because if not, it's not a huge deal, but stop me if, because I'm making all sorts of gesturing with my hands, okay? So vertical, transverse, radial, and so what was I saying? So if you have a wave, okay, that travels from if you look at from the receiver, you look at the source, the transverse wave, it moves, and here you really have to see me. So stop me if that's not the case. So the transverse wave would entail a motion like that, okay? It's transverse, perpendicular to the direction of propagation. The vertical component is also perpendicular to the direction of propagation, but it goes up and down, okay? Yeah. And radial, it just points to you. So, all right. Now, so what does this seismogram tell us? It tells us basically that there's something that is basically the same disturbance that basically involves a radial and a vertical component, because you see it's the same thing, right? It's the same wave, it's the same sequence of oscillations on the vertical and radial component. It's unlikely to be a coincidence. And if you looked at hundreds of seismograms, you would see the same thing over and over again. The same effect, not the same thing, but the same correlation between vertical and radial component. And the transverse wave has, it seems to be faster, this feature here. And see, it arrives earlier. This is time on the horizontal axis, of course. So it arrives earlier at this location at 110 degrees. And it doesn't look anything like what we see in the vertical and radial component. So what does that mean? Well, the explanation, which is not trivial, but required many years of, at the beginning of the last century, of increasingly accurate observations, people finally came to the conclusion that there must be 2 types of surface waves, which they were then called Rayleigh wave and log waves. The Rayleigh waves involves, I think it's called retrograde motion. Yeah, I didn't write it. It doesn't really matter, but basically it involves, if you follow a particle, okay, that's hit by a Rayleigh wave, it moves in a circle like that, okay? So a Rayleigh wave looks very much like a wave in the ocean, actually, in a first approximation, except that, and it would be very complex to explain or mathematically why, but we are able to do that now. if you look at the motion like that, for the Rayleigh wave, you have a counterclockwise motion. And for the wave in water, okay, the surface wave, it's actually a surface wave, okay, the tsunami wave, in the water, you get a prograde, you get clockwise motion, okay? So that, but it's kind of the same story. Right. Okay. And then there's another one, and so the Rayleigh wave. Why this motion? Because that would be the wave that propagates both in the vertical and radial direction. If you put vertical and radial oscillation together, you can get something like that. Okay, it's both radial and vertical, but there's no motion in the transverse. There's no motion. See, in agreement with the data, there's no important motion associated with this phase on the transverse direction. Okay, and so in the transverse direction, we have another motion that's decoupled from the Rayleigh wave, and that would be something that we call the love wave. The reason for this name is historical, and I think it's worthwhile to think about how all these concepts came to be. Initially, when people started looking at seismograms, they didn't have, I'm talking about the end of the 19th century, so they didn't have very good instruments. So it was very hard to disentangle all these phases from one another. They realized that there was some sort of initial, they called it a preliminary tremor, okay, that was often separated into a P, and the S here is fairly hard to see, but usually you would have a P and the S arrival, which, if you are at a distance from the epicenter, are kind of small. So they were called preliminary because the big one, the large displacement would call later, and that would be the surface wave. But initially, the theory that was developed by Cauchy, Poisson, Stokes, etc., in the middle of the 19th century, didn't really predict. It didn't really, predict these surface waves. It was only Rayleigh, Lord Rayleigh, at the end of the 19th century, who mathematically figured out that if you have a free surface, you will end up having a disturbance like that propagates along the surface, like I explained the other day. And it's interesting that when Rayleigh came up with this idea, initially it was not clear at all whether he was right and whether seismograms would actually be in agreement with what he was saying, partly because there was this problem that depending on which component you looked at, the surface wave would look very different. And it was only when Love, at the beginning of the 20th century, further perfected the theory that then people realized that there are two types of surface waves, that they are expected mathematically, and as better measurements, better seismograms became available, they also started to see these two phases in the data. But Rayleigh and Love, interestingly, are the people who, they're not observation people as much as they are theoreticians, and they came up with the theory that would demonstrate that such waves should exist, and then based on their ideas, by looking at seismograms, it became increasingly clear that indeed the data would confirm the expectation of the theory. So anyway, so it would be very time consuming, even if I had more time, to go through both Rayleigh and Love derivations. There's plenty of book where you can find those if you're curious, if you need to understand better. But what I'm going to try to do today is to give you a feeling of how math can help us to predict the existence, to demonstrate that these waves should exist. And I will do that for the simple case of the Love wave alone. The Love wave is simpler for the simple fact that it involves only one component. Okay, if you place yourself in a reference frame where one of the axes is the vertical axis and one of the horizontal axes is aligned with the direction of propagation with the source station line, then you can simplify the calculations quite a bit. And that's precisely what we are going to do. So I should stress once again that, as you see in the drawing here, you have to think that this this flat surface here on top of these diagrams is the outer surface of the Earth. You see that the amplitude of the displacement dies away as we go deeper into, as we look deeper into the Earth. And that's the same for both the Love and Rayleigh wave. They are surface waves. This is why they're called surface waves, of course. So from the point of view of mapping the structure of the Earth, surface waves are very useful to constrain relatively shallow structure. Depending on the period, like I was saying the other day, depending on the wavelength, we can sample more or less deep. This signal will sample more or less deep into the Earth, and in turn, it can be used to constrain structure at more or less large depth into the Earth. What I mean by that is that if a long period Rayleigh wave propagates slowly in a certain regions, we might infer that at some large depths under that region, there is some area where shear velocity is low. If we have a higher frequency Rayleigh wave in the same place that's faster than average, that's faster than expected, we would infer that it's actually at some relatively large depth that the structure is low, while at the shallower depth to which this fast high frequency wave is sensitive, structure would be probably faster than average. This is important because if you think teleseismic wave, teleseismic distance, if you think large distance, if you think the global Earth, body wave, they sample deep into the Earth, okay? Remember, you've seen probably this before in geophysics course, the typical path of a body wave. It goes deep into the Earth, it's refracted because structure becomes faster and it comes back up at some large distance. So unless you can put earthquake and stations everywhere on the surface of the Earth, which you can, because earthquakes are on plate boundaries and stations are on continents, you will have large areas where basically data cannot sample at all. And that's where surface wave help you, because surface wave actually can cover precisely those areas that body waves don't see. Okay, so if you start thinking in terms of tomography, you see that body wave and surface wave data are highly complementary to one another. So to figure out some mathematical representation of love waves, we start with what mathematicians might call an ansatz solution. So, you know, and we will see if this ansatz solution indeed satisfies both the Navier-Stokes equation, which I rewrote here, and the boundary conditions, which we look at in a second. So what's a love wave? A love wave is if we put ourselves in a reference frame where the x2 axis is parallel to the direction of propagation, then the love wave is I want to get rid of all these edits. So the love wave is a displacement that propagates in time like a wave. So see here the typical argument with space and time in such a relation to one another, so that we make sure that this is a wave. The radial and vertical component x1 and x3 in this reference frame are 0, and all the signal is on the transverse component. Okay, so we make sure that all the signal is here, and this particular phase has no it involves no displacement in the radial and vertical direction. And then let's look a bit more closely at the signal here. So you see, there are two things that you have to remark. The first is that we separate the x3 dependence, the vertical dependence on depth of this displacement from the horizontal dependence. The wave propagates in the x1 direction, and if you I don't remember if we looked at direction of propagation in 3D. We probably didn't, but if you do a little bit of algebra, you can convince yourself that basically this is something that travels in the x1 direction. It doesn't, the displacement changes as a function of x1 at a given instant in time, but not as a function of x2. Yeah, that's probably the. So I should probably spend a couple of words on that. Yeah, let me see. Yeah. Yeah. Okay. So incidentally, something that probably I should have clarified before, in the we looked at wave propagation in the string. Okay, and you remember that in the string the solution has an argument, is a function with this argument, right? And the speed of propagation is given by omega over k. now, if you are in 3 dimension, the solution, it's basically the same thing, except that we are in 3 dimensions. So if you want to write it in, let me strange. I've never had this problem before. So if you want to write it in vector notation, it looks like that. Or if you prefer the scalar notation, it looks like this. And if you fix time, so at a given instant in time, this is the equation of a plane. Okay, and what does that mean? It means that if you watch the propagation of the wavefront, okay, of the locus of all the points that are experiencing the same disturbance at the same time, you see a plane that propagates across space. And
sorry, sir.
Yes.
K is a constant or function. I don't understand K.
Yeah, sorry. What I'm saying is that if you take a picture, so if you think of the question basically that I'm asking, sorry, I'm improvising a little bit, but the question I'm asking, what's the locus of all points that experience the same disturbance at the same time? Okay, so to think, to simplify, to fix ideas, you can think about the simplest possible way, which is an impulse. Okay, and it looks, it could look like this with delta, the Dirac delta. So in that case, this equation would basically identify the points that are moving at a given instant in time while the rest of space is not experiencing any disturbance. So if you fix T, they form a plane, okay? K1 x1 plus K2 x2 plus K3 x3 equals a number is a plane in 3D.
Okay, sir.
Isn't it?
Okay.
Yeah. So if as time passes, the same equation holds, but this number changes, and so this plane moves around. Okay, and the direction in which it moves is given by this vector k. Okay, so if this is a plane wave, okay, for a spherical wave, it's the same thing, except that here instead of x, you have r, And so actually you get, it's not exactly the same thing. You don't have a scalar product here. In the case of a spherical wave, you would have R minus P over C. And so that would be a sphere. But you don't need, we don't need now to think about that. We are, for surface waves, we are sticking to plane waves to keep it simpler. We are not getting into cylindrical surface waves, okay? So now, yeah, now, in the case that I am considering, it basically K is K1, sorry, it is 0, K2, 0, which means basically, sorry, it's, we decided that it propagates in the X direction, not Y. So it's K1, 0, 0, which means that no, this, voila. Okay, which means that the propagation is in the x1 direction, and this part can be neglected. Okay, so that was a bit fast, but let me stop me if it wasn't clear enough. Sounds okay? So that now we understand a bit better what this means. And there's one last thing that you have to remark in this expression, and that see, let me show that to you in the blackboard here. When I write the argument such as this, I'm specifying this frequency omega. Okay, it means what I mean by that is that this is a monochromatic plane wave. This omega has the meaning of frequency in time. Okay, so it's the underlying idea when, and you will find it in a lot of textbooks. Okay, they give you the solution in terms of monochromatic waves at a fixed frequency omega. The idea is that by Fourier analysis, which we touched very briefly upon, you can always represent any signal as a sum of monochromatic waves. So if you solve a problem for a monochromatic wave of arbitrary frequency, implicitly you solve the problem for any wave, because any wave can be written as a combination of monochromatic waves, as a linear combination of monochromatic waves. All right, so a wave that has signal only in the transverse component. that has a signal that dies away with depth. Well, I haven't said that yet, but has a signal that might change in amplitude as a function of depth, but it propagates along a horizontal direction. So there's no x3 in here, only there's no k3, only k1, or there could be k2, but we could have some direction that is not that is not parallel to x1. It's still on the surface of the Earth, but we don't care because we can always pick, so long as we work only with plane waves, we can always pick our reference frame so that the x-axis, the first axis, is parallel with the direction of propagation. And it's a monochromatic wave. Okay, so we specify a frequency omega. You've seen this before. This is Hooke's law. So we assume that the medium is elastic. That shouldn't surprise you. But then, and here is where I'm going to go a bit quicker. Since we are considering a particular phenomenon that we know from the data should exist, and it only involves motion in the x2 direction and not depending on x2 itself, motion like this, then or basically, in other words, if you substitute this expression 1 into expression 2, a lot of these derivatives here and here and here will be 0, because some of the components of u are always 0, and because the second component doesn't depend on the second coordinate. And so basically the Hooke's law can be simplified to this more attractive form. Another way to put it basically is that this is divergence free, since there's no component in the direction of propagation, all we see here is shearing, and there's no compression or expansion, so divergence here, which is what you see here. Okay, it's the uk over the xk, implicit sum over k is the divergence, and it's got to be 0. Okay, and so here you have the Navier-Stokes equation Navier equation that you know, and if you plug this guy into Navier, you get that. But again, this can be simplified a bit because a lot of these derivatives are 0, right? Because of the peculiar character of u in our ansatz. And so eventually the equation boils down to that. So the other equation for u1 and u3 are irrelevant because u1 and u3 are identically 0. And we are left with one scalar product of determining the only non-zero component of displacement. Okay, the next step, is this okay so far? The next step would be to apply, as usual, now we have the ODE or PDE, actually, in this case, that we want to solve. We also need to specify some boundary conditions. This is particularly important in this case, is we're looking at surface waves, which are a product really of a boundary, okay, that this free surface. So I'm not getting into the details of that, but log waves, to obtain log waves, you need more than just a free surface, you also need at least one discontinuity under, at some depth under the free surface, below the free surface. Love waves only emerge when you have at least a layer over half space situation. This is obviously the case in the Earth, because the Earth has, at the very least, we know by now that it's got the Mohorovic discontinuity at some, I don't know, 10, 20, 30, 50, 80 kilometers, depending on where we are standing on our planet. There's even more discontinuities than that. So the Earth is at least also laterally, but most of all radially heterogeneous medium. So a layer of the half space model is reasonably realistic, and it's certainly not, it's an oversimplification rather than a complication of what we observe in reality. The Earth is basically layered, okay? Velocity grows with that. So this is obviously not crazy to start with a model such as this. If we didn't have discontinuities within the Earth, if elastic properties changed very smoothly with depth or were uniform, then we would not observe log waves. Okay, this is, I'm sort of just telling you at this point. One could also give a mathematical proof for that. That's basically the reason why it took, I don't know, some 30 years between the discovery of Rayleigh waves and log waves, I think, because Rayleigh waves, you know, if you do the math with the simple model like Rayleigh did, okay, just a half space, you get Rayleigh waves right away, and that's all you get. The solution doesn't show any surface wave, any transverse, any log wave. Sorry. To get the log waves, you actually have to prescribe a discontinuity also at some depth, and that's what Love did in, I think, 1911. Okay. So, and we are going to do it right away because this is a short course. It's not a long course. So in such a very simplified model, we can apply all the boundary conditions and see if our ansatz solves the problem. First of all, before actually we go ahead with the boundary condition, we can, I mean, with the mathematical form of the boundary conditions, we can already reason a little bit about this equation. It's you recognize it, right? This is the Laplacian minus the x2 derivative. It's another form of the wave equation. So, but we have our ansatz that we decide that we want to try. Ansatz, you know, it's just a mathematical jargon thing. It just means a trial solution. It means that we make a hypothesis and we see if it works. So does our hypothesis work? Does our ansatz work? We plug this expression here, equation 1, into the PDE, the partial differential equation that we came up with, that if we solve it, we solve our problem. And if you do that, see, you have an exponential here, right? So the derivative of the exponential is the exponential itself multiplied by the factor here that multiplies whatever variable you are differentiating against. So if you differentiate with respect to x1, you get k. If you differentiate with respect to omega, to time you get omega. And so then this term, it stays. So eventually it cancels out and you're left with this expression. The beta here is just, you get it by, beforehand, you should divide both sides of equation 6 by rho. Okay, so you bring rho to the right-hand side here, divide both sides by rho, call beta the square root of mu over rho, and you get, and after substituting the ansatz, you get this expression. Why do I have B1 and B2 here? Well, because I told you we are doing a layer over half space model. So before we apply the boundary condition, implicitly, we are solving our equation in both layers of our model, 1 and 2. This equation, the way we've derived it, it has to hold no matter in which layer we are, until the discontinuity comes into play. The math and the physics are the same, and this guy has to hold. So the strategy is to find a solution to this equation, and then to see that by choosing some appropriate value for its parameters, it actually satisfies the boundary conditions. Okay, so there we go. Now, again, here you have well, no, this is called, it's not the wave equation anymore. It's called the Helmholtz equation, in case you like to remember these names. But it doesn't matter. You're looking, what this equation says, it's we are looking for a function whose second derivative is proportional to the function itself. And we've met it before. We've met it in the case of the string, right? After we've done separation of variables, both with respect to time and with respect to space, our t and x functions, or tau and psi, had both to satisfy this equation. So the solution, again, it's some sort of exponential. And here we go. Okay, it's easy. You can do it as an exercise to substitute this expression in equation 7 and verify that it verifies equation, that equation 7 is indeed verified. I mean, take the second derivative of this guy and verify that what you get is exactly the right-hand side of 7. All right, so of course, you know, this is just h, so you have to substitute this into the ansatz expression to find u, to find the displacement. You know what? I'm going to send you. It's stupid that you don't have my PDF. Actually, I'm going to send it to you right away. I was thinking I send it to you later, but I might as well send it to you now. So, of course, that requires, yes. So I'm just going to copy paste it in the chat. And hopefully you're able to download it, and you can, if you use some sort of PDF viewer that allows you, as I do, to make comments, you can take your notes directly on the PDF. Maybe that helps, maybe not, it won't hurt. Okay, if you have it right away. Okay, you should be able to download it by just clicking on it in the chat of this lecture. All right, so now we have this general solution. Okay, you should be able, if you have some time this weekend, to take its derivatives with respect to time and distance and verify that it does satisfy our partial differential equation. It's not very different from exercises we've done before. And now the next step of the exercise, after we are all agreed on that, is to apply the boundary conditions. And there are two boundary conditions, actually three, because there's also one thing that I haven't mentioned. You don't want large displacement for large values of x3. You don't want anything to happen when x3 is very large. x3 is the coordinates that's 0 at the surface of the Earth and grows as we go down. It's depth, basically. So physically, it wouldn't make any sense to have large displacement at infinite depth. So that we can think of that as an additional boundary condition. And then, of course, the boundary conditions that we mentioned before. No stress at the outer surface, and continuity of the, continuity of displacement and tractions at the interface between layer and half space. All right. So the first boundary condition is satisfied if we require either that the real part of this guy is negative, or the real part of this guy is negative. I mean, it's the same thing, right? Only the sign changes. So we have to decide whether the boundary condition boils down to this, the real part of this is a negative number, or the real part of this is a negative number. Both things cannot be true at the same time, right? So we have to pick one, and we pick the first option. So we require that the real part of the number that multiplies x3 here is negative, which means that the square root here is positive. Okay, and if that's the case, then in the this coefficient has to be 0. I'm talking, of course, about the half space only. Okay, I equal to the lower layer, because x3 doesn't go to infinity in the top layer. It's bounded between 0 and h, which is the depth of the interface. So I don't have to worry about this condition in the top layer. The condition 2 requires that outer surface be free of stresses, and that, of course, it can be written that at x3 equals 0, the three components of the stress tensor have to be 0. It's like the fact that u1 and u3 are 0, and again, you can verify this as an exercise, but that immediately implies that tau 3.1 and tau 3.3 have to be 0. So we are left with only one condition at the outer surface, which is a condition on the remaining component of stress. And I'm talking not about all the 9 components near the surface, but about the 3 components that act on that very surface, okay? So it all boils down to this guy who's proportional to del U2 over del X3 being 0, or basically del U2 over del X3 equals 0. We have an expression for U2, so we can substitute it in here, and we get this equation here. Okay, nothing magic in here. I'm just imposing. That's what I do when I impose a boundary condition. I have a general expression for the solution, and I require that it satisfies the boundary condition, and I see what that implies for the arbitrary parameters that are contained in this equation. Okay, so this has to hold at all times t and at all location x1. So this can cancel out, and basically for this to be 0, we have to have that A1 equals B1. It probably would have helped to stress that if I had emphasized a bit more, if I had stressed a bit more that in this general solution here, as usual, you have as to be expected for a second order equation, you have two arbitrary constants, okay? And since we have a layer and a half space, with these boundary conditions, we have to constrain 4 arbitrary constants. On top of that, K is sorry, omega, not K, but omega is a parameter that could in principle also only, just like we've seen for the string, okay, where frequency could only take a discrete set of values. A priori, we might find the same effect, and obviously, if I mention it, is because we will, okay. But so by applying the boundary conditions, we are going to reduce this very general expression here to a more restricted set of functions that are allowed to exist in our layer over half space model. Okay, this is what I'm doing. You know, I could also, in principle, I could also have stopped here, and I could have said, okay, well, so yeah, this satisfies the Navier equation, and so we are good. But it's not very interesting, right? You want to make sure that you satisfy the boundary conditions, and even more important, you want to see what constraints the boundary condition resulting for the surface waves that you expect to observe in the real world. So the first of these constraints is that A1 equal B1. Okay, so that simplifies the solution a bit, and we are left with the displacement having to coincide in the top layer. Okay, because these are conditions applied in the top layer. It has to coincide with this guy, and in the bottom layer, we applied our condition to what happens, and if infinite depth, it has to look like that. Okay, so we have bottom layer, or I should say in the half space. Okay, so we have U2 that takes either of these two forms, depending on whether we are in the top layer or in the half space. Okay. So finally, we are left with the more complicated conditions, which is the condition that everything be continuous at the interface. We don't want, we don't expect a propagating surface wave to open a cavity in the internal structure of the Earth. All our theory, remember, it all works for small deformation. If deformation is not small, even Navier equation is not valid anymore. So we must we actually would have to rethink our theory altogether. But luckily enough, unless we are in the immediate vicinity of a fault, that's not the kind of thing that we observe in the Earth. So we are content with restricting ourselves to relatively small deformation, and immediately that requires that we requires that we impose, that we prescribe continuity of displacements and continuity of tractions, continuity of the stress tensor at the bound.
Sorry, sir.
Yes.
Equation 11.
Yeah, I see that someone probably you sent something. So equation 11. Yes.
Not the. Can you see my PDF?
Yeah, the I is not supposed to be there. Is that? That's a typo. Is that what you're asking?
Yes, sir.
Yeah.
Yeah.
Yeah, I think you're right, actually. Finding that in such a long time, I haven't. Let me check, actually. Is this a typo? No, I don't think it's a typo, actually. Now that I think about it, sorry, because I think it's okay. I think I'm right, because here you don't have I. So this guy, it will be cosine of chi x minus omega t plus I sine blah blah blah. But here actually it's kind of weird. I know maybe it's not the best way of doing it, I don't know, but here I don't have any I. Okay, so if I want to translate it to a cosine, somehow I have to put a imaginary unit in the cosine. So I'm trying to think if I can I find yeah, I don't know if I can find yeah, there we go. So excuse me, as we speak, I'm quickly looking for these things. So give me a sec. No, share screen. Safari, Euler's formula, Wikipedia. So I apologize for using Wikipedia, but I love Wikipedia. So see, all I'm doing is I'm applying. So instead of applying this formula that we tend to use more often, I'm applying this formula here. Okay.
Okay, so thank you.
All right. No, thank you. You're right. It did look kind of suspicious, but and you almost for a second I was convinced myself that I was wrong, but no. Okay. Allora, let me share the right screen, the right thing. All right. So here we go. So, you know, all these things look very crazy, like the cosine of an imaginary number. It's really all, it's just a way to do like the bookkeeping, to keep track of things without having huge formulas. Okay, I could avoid writing these like this if I kept this longer expression here, but then you know, it's cumbersome, and I'm trying to compact things somehow. Anyway, we apply, and this is where it gets heavy, analytically, algebraically. We apply the conditions in the continuity of displacement. So you see, we have on the left-hand side, we have the displacement above the discontinuity. At the right-hand side, we have the displacement below, and they have to coincide because that's what the boundary condition is telling us, right? So here we go. So somehow A1 and A2 must verify this relationship. And then and here I'm really skipping all the math because it's just heavy. But if you essentially implement where is it that I write it down? Where you implement the continuity of this guy, so you have to calculate the differential, the derivative of both this guy and this guy with respect to x3, and then equate them together. You get this horrible thing here. And so what you have now is a condition. You have two conditions, two algebraic equations that you can use to identify values of the so far free parameters that can satisfy our conditions. So A1 and A2, like I said, for sure, but also omega and k. Everything else is prescribed, right? Because we have an Earth model. We think that that's our best guess as to what the structure of the Earth is like. So we assume that we know beta 1 and beta 2, which, if you remember, are basically just shear velocities in the two layers. We assume that we know h, which is just if you will, it's just the depth of the Moho. But we can find a range of suitable values for A1, A2, and also omega and k. And so the one way, and this is what you find in some textbooks, okay, one way to attack this problem is to take the ratio of equation 13 and 14. If you divide, well, or actually take the ratio of the left-hand side of the right-hand side of 13 to the left-hand side of 13. Okay, you divide both sides of this equation by the left-hand side. No, you divide both sides of this equation by A1 and by this term here. Okay, and you are left with this. This is the ratio of A2 to A1 based on equation 13. And then you do the same trick on equation 14. You got two different expressions for the ratio A2 to A1, but their values must coincide, right? So you equate them to one another, and basically you have the same information that you had above, but you just manipulate it in a form that you can play around a bit more with. You see, if you compare the left-hand side to the right-hand side of 15, sorry, here you get the cosine of this angle. Here you have the sine of the same angle. So again, if you take the ratio of these two, of the two sides of this equation here, well, if you divide both sides by the cosine here, you get the tangent. Okay, the ratio of sine to cosine is tangent. And then if you do the algebra, this will leave you this expression on the right-hand side. Okay, so this equation starts to look like something that one can solve with a calculator or with some tables for the tangent or whatever. And if you substitute k with with omega over c and do a little bit more algebra, you can write the same equation in this form. And again, you see, you play with this I here, and if you can bring the I within the square root, it becomes, I basically means -1 squared. So ultimately, you are left with this equation. And the algebra, I'm totally aware that it's heavy, and I'm not expecting you to follow every single step, but I'm trying to give you a guide so that if you want, you can think about it on your own and rederive it. But the important point here is that see, you basically, there's no way to solve this equation analytically. You're not, I don't think there's a way. Of course, you can say that this guy equals the arctan, that this angle here equals the arctan of all this stuff, but that doesn't really help you understand what's going on. What helps you is to think of it, as we might say, numerically or graphically. That is to say, you can, and this is what you'll find in textbooks like Aki and Richards, you plot in a graph the right-hand side of this equation in a graph where on the horizontal axis you have the argument, except for omega, of the tangent. Okay, so you plot everything as a function of the argument of the tangent, and you see that with a small transformation from whatever value you have on the x-axis, you get the value in here. So you can basically graph how the right-hand side of that equation behaves. Anyway, you see what I'm trying to say. Okay, it's this guy here, and then you do the same thing for the left-hand side, which in this case it's simple because that's the argument here, and it's just a tangent. Okay, I can even draw it with this stupid method here. And so on and so forth. And the tangent has this periodic behavior, right? So depending, and basically you here we've been plotting it between the values of beta 1 of C, of the value, sorry, of this argument that correspond to where you would actually find some intersection. Outside this argument, basically everything becomes complex, and we don't have physically meaningful solutions anymore. The point of all this is that for the equation to be verified, the left-hand side and the right-hand side have to have the same value for a given argument of the left-hand side. So basically, you only have solutions at the intersections of these two curves. And that's a very important step to understand, because it brings us to a very similar situation as we've encountered when we were studying the string. When you solve your differential equation, you have a continuous spectrum of possible solutions. Okay, this is an infinity of solutions, and A, B, omega, K could have any possible values. But the moment you apply the boundary condition, this freedom is gone, and only a discrete set of values of these parameters become acceptable. We are not looking at A2 and A1 here, which would require to be constrained by initial conditions later on, but the boundary conditions, they, as you have seen, result in some constraint on basically the parameters that are involved here, which are omega and K. Okay, K equals omega over C. So whenever I write C here, I'm basically writing K. But the reason I prefer to write C, and I should have mentioned it later, is that omega over K has the meaning of a velocity of propagation, right? If you remember the math that we did earlier, and the argument of the traveling wave. Okay, so what we have here is what the boundary condition is telling us, to make a long story short, and this is the one important message that you really have to take home, is that a surface wave in a given Earth model can only propagate at a discrete set and even finite set of phase velocities and frequencies. Okay, those are the values that corresponds of omega and C that correspond to intersections between the left-hand side and the right-hand side. So the bottom line is that just like we speak of eigenfrequencies and eigenfunction or normal modes and normal mode frequencies in the case of a string, for the case of the free oscillation of an elastic body in general, also in surface wave we have modes. Okay, you will hear people talking about the fundamental mode of a surface wave. the fundamental mode of a surface wave, which incidentally is the mode that in the real world carries the most energy, at least for faraway quakes, is in this diagram is the mode that corresponds to the lowest possible frequency. Okay, and then just like you have overtones on the string, you have surface wave overtones. Okay, so oh, I mean, yeah, I guess if it's a hyperbolic cosine, it's probably okay. We are probably saying the same thing. Sorry, I saw your comment. I saw a comment from one of you only now. So this sounds like quite a few things for you to think about. There are yeah, there are a few more. There's one more paragraph, one more section in the notes that I sent you, where I briefly explain dispersion and the concept of group and phase velocity. I would prefer that you read it on your own and get back to me if something is not clear, because I'd rather not do it in 5 minutes, okay? But it's much easier. These final concepts in the script are much easier than the stuff I've tried to cover this morning. Basically, to really, in a nutshell, if you want to think about it empirically, you see that essentially you have a connection here, like the velocity of propagation depends on frequency. That's pretty clear. C is omega over K, omega is frequency. So what that means in practice, when you look at the data, is that you will meet a pattern like this, where here you have a bunch of different seismograms stacked near one another, each associated with a different distance between source and epicenter, and distance growing with the vertical axis here. So what the author here has been trying to show is that, like, usually in a surface wave, the low frequency signal comes earlier, and it's followed by higher frequency stuff. And low frequency is faster, and which means that if you wait, if you stand at a larger distance from the epicenter, the time that passes between the arrival of the low frequency part of the surface wave and the high frequency part is longer. Okay, so the phases associated with different frequencies are farther and farther separated in time as we stand farther away from the source. And this is a phenomenon that's called dispersion. It's important, I think, practically that you realize that in seismology, when you look at body waves, that dispersion is really an almost negligible effect. I would say that you don't really see the important dispersion in body wave data. But surface waves are very dispersive. And this dispersion is not inherent to the elastic properties of the medium. It's associated with the fact that with this depth dependence of the surface waves that I mentioned before. Why is it that long wavelength or low frequency, long period surface waves are faster? It's because they sample deep into the Earth. It's because they have a long wavelength. It's because they entail the displacement of a big layer, of a big chunk of Earth material. And deeper into the Earth, shear velocity, compressional velocity, seismic velocity are higher. So the surface wave, which basically average, a long period surface wave, which is basically an average, okay? It's sensitive to an average of Earth properties over a broad range of depth. It's affected by the elastic properties of the deeper Earth, and so propagates a bit faster than the high frequency surface wave that's confined to the top of to the depths that are near the surface of the Earth. So I would like you to go carefully through my lecture notes for today, even if to be patient, even if this lecture was a bit more concentrated than the rest of the course. I think we covered pretty much all the material that you need to have for the courses that will come next. You won't see me again in this format, but feel free to contact me with an email at any time if you have questions, and you'll hear from Karima Audia concerning the exam that I will prepare for you. Okay, so I haven't prepared it yet. I will probably do it early next week. So I don't know what will be in it, but I try to be kind. Okay. Anything that you would like to share? Any questions, or should we call it a day? And I leave you to your work. Okay. All right. See you at some point.
See you
yeah,
soon.
yeah. Thank you very much, Guy. I hope
Thank you, sir.
Thank you, sir.
Thank you.
Bye.
Yeah.
Bye.
Bye. Ciao.
Ciao.